Okay, welcome to Chemistry with Mr. Brazil. I'm going to teach you how to write up electron configuration. I will teach you three different styles. Let's start with some basics. First of all, we have our traditional periodic table here on the left-hand corner, and each square is like a seating chart for an electron for a particular atom. And what we do is, hopefully your teacher has discussed what an s and p and d orbital, but if you go to the right here, this particular periodic table follows the traditional one. And so S block is the first two columns, and an s orbital has a spherical shape, and there's only one orbital. And the way we can determine that is we take the columns. So since there are two columns for the s orbital, 2 divided by 2, that equals 1. So there is one s orbital. And if we look at the p, and notice that the p starts at 2, not at 1. So it always goes up an energy level. So there are 6 columns here in the p. So p, if you take 6 divided by 2, and the reason we divide by 2 is because Pauling's principle only allows 2 electrons per orbital. So we're going to have 3 orbitals. So a px, where it's a dumbbell shape, that's in the x direction, a py, which is in the y direction, and then a pz, which really kind of comes out at you, one lobe facing out the screen and one inside the screen or behind the screen. Then you have d orbitals, which are all kinds of shapes, but since there are 10 squares, or 10 columns, I should say, divide that by 2, you're going to get 5 orbitals. And f, which is the intertransitional metals, they actually fit in between here. If you look at this periodic table, that old traditional table is due to Seaborg. He stated, hey, let's pull out the F block. If you go down to the lower left, you'll see in green the F block sliced in there or spliced in there. That's where it actually belongs. The periodic table is actually a long table. If we had a G block, it would go right in this portion right over here. So Seaborg suggested pulling it out, and now it fits the traditional 8:11 ratio aspect kind of, so it fits nicely in a classroom on an 8:11 piece of paper. But going back to the F block, if you count, there are 14 columns. Divide that by 2, you're going to get 7. And you begin to see a pattern that everything is going up. You add 2 to 1, you're going to get 3. You add 2 to 3, you're going to get 5. And then if you add 2 to 7, if there was such thing as a G block, now you're going to have 9 orbitals. But since that doesn't exist as of yet and doesn't look like right away, nothing to worry about. So what I'm going to do here, let's go on to another slide and let's start showing you how to do the orbital configuration. And orbital configuration takes into account electron spin. So Aufbau stated that you have to fill in all the lower energy levels first. Hun, if you have more than one orbital, you first put an electron in each orbital, and then you start pairing them up, which Pauling, the exclusion principle, says, hey, you can only have 2 electrons, but they must have opposite spin. So we will learn how to draw that right now. So let's take into account lithium. Lithium is in the second row. So to write the orbital configuration, first of all, lithium has 3 electrons. So there are, if you even count, there are 3 squares, and I'm going to go row by row until I get to the particular element of interest. So let's take a look at this. So I'm going to go row by row. That means I'm going to go 1s, since the hydrogen and helium are in the 1s block. So 1s, and an s orbital has only 1 orbital. So 1 electron spinning up, and if I start up, I always go up. So 1 spin up, then I go to the helium, the second electron. So there are 2 electrons in that s orbital. Now I go to the second row, and now I'm in 2s, again 1 orbital, but since lithium has 3 electrons and there's only 1 square, it took 3 squares to get to lithium, so 1 arrow up. So 1 up, and that is the orbital configuration, the electron configuration for lithium. Now, let's try something a little more complex, a little longer. Let's take a look at, let's say, titanium, Ti. So Ti. And then I'm going to go row by row, cycling down to lithium. So here we go. I'm going to go 1s, a dash, because I'm starting at the hydrogen and working my way over. So 1 up, 1 down. Now I'm at the second row, so I have a 2s, okay, and it's going to go right through the lithium and to beryllium, so 1 electron up, 1 electron down, okay. Now I go clear over to the p, and the p starts at 2, so each new orbital is at a higher energy level, so it's going to be 2p. I have 3 dashes for x, y, and z. So there are 6 electrons in these particular squares right here, going up because I'm not at titanium yet. So 1 up, 1 up, 1 up, down, down, down. Okay, so now I've put my electrons in for the 2p. Now I go right down to the 3. So 3s. And I'm going to go through the sodium and magnesium. So 1 up, 1 down. And now I'm at the 3p level. So 3p, 3 dashes, 1 up, 1 up, 1 up, and now I'm going to put the other 3. Okay, so that's all 6 electrons put in. Now I cycle down. I am now in the 4th energy level, so it'll be 4s. I'm going to put it right here below the 1. So 4s, 1 dash, so 1 arrow up, 1 arrow down. And now that scandium starts the 3D. So that's a 3D row. So this whole row is the 3Ds. So it's going to be 3D, and it's 5 dashes, if you remember from the earlier. 1, 2, 3, 4, 5. I write those down. And then since it takes 2 squares within the d orbital range, so 1, 2 is 1 electron up, 1 electron up. I don't pair them up. We're following Hund's rule. We first put electrons in each orbital. So this is kind of how you write the orbital configuration. Now, for electron configuration, excuse me. This can get really long-winded. It can get complicated, especially if you go into these much larger elements below the periodic table. So let's go to something a little easier, and then eventually we'll get to something much, much easier called the noble gas method. So let's go on to the next slide. All right, so let's do the long hand electron configuration. Okay, so longhand, here's how this works. Instead of dashes and arrows to show spin, which is fine, if you're a theoretical physicist, chemist, you might want to do something with that. But if you want to kind of know where the electrons are arranged, or maybe figure out paramagnetism or something like that, you could just work with this. Let's take, in this case, let's go for iron, Fe, number 26. 26 electrons. So Fe, it has 26 electrons. Okay. And again, I'm going to cycle from hydrogen and work my way down. So I'm going to write 1s, but this time I'm not going to write a dash. I'm going to use a superscript. And since I'm going from the hydrogen to the helium, 2 squares, 2 electrons, so 2 electrons are placed on the 1s. Now I cycle to the 2s. Again, I'm going through the lithium to beryllium, so 2s. I'm now at the 2p, 2p. Now all 6, so 2p6. Now I'm going right through the sodium and magnesium, so that's 3s, 3s2. So hopefully you're beginning to see a slight pattern. There's an arrangement, a flow to this. So now I'm in the 3p. I'm going to be going right through that whole row, so 3p6. Now I'm in the 4s and 4s2. And now I'm in the 3D block, so 3AD. And now I count 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6. There are 6 electrons, okay, in the D block. And that is my complete electron configuration for iron. And that's simply done like that. No dashes, you can see it fits nicely. So hey, let's try something, a little different. Let's try for hafnium. Let's try to write the electron configuration. And the reason I want to do that is because if you look at this purple row, it fits right in between there, and we have to take that into account. And not only that, lanthanum and hafnium are D blocks. So I'm going to show you how to put that all together so it works out nicely for you. Let's get rid of some of this stuff right here. Okay, so that it's cleaned up a little bit. Okay, so let's go for hafnium. So HF, that was strange. So HF, hafnium, we're going to have 72 electrons all together. That's quite a bit. Here we go. Well, we're going to cycle down and notice that this pattern that's for iron above, right here, is going to show up below. 1s2, 2s2, 2p6. Yeah, it's the same thing all over again. And it begins to be a little quick to do this because here I am, hafnium's way down here. So I have now 3p6, 4s2. I'm right here at the 4. I'm going to go through 3d, 3d10. Okay, and now if I get confused, I can just go back to the P block. I go 2, 3, 4. So I'm now at the 4P and 4P6. Oh, notice this. Isn't this kind of interesting? There is a pattern that's going to start occurring from below here. You'll start seeing that when we go to the 5S, we're going to have the 5S and a 4D and then a 5P. It kind of cycles that like that. It doesn't get too much complicated. So once I'm through with the 4P, I'm in the 5S. Let's change the color again back. So 5S2, 3, did I just say 3? Okay, we're in the 4D, 4D10, and 5P6. Notice how I was able to correct myself. Now, we're at 5P6, so cycling our way down, we're now at 6 S2, and now we're at the 5D, but since this D right here, the lanthanum, if you could look right up at the periodic table, and hafnium are in the D block, those are 2 electrons there, so that's a 5D2. So let's put 5D2. And then I'm going to squeak in this, now looking again at the light purple, I'm going to squeak in that block in there, and I'm going to put 4F14. Okay? So that 4F14 could be put right in between the 2 right on this end, but I'm leaving it like this. And this is the longhand method. Wow, this can get really tedious. It can get a little crazy. So the best method that I tend to like is the shorthand method. Let me show you how that works. Okay, and I'm going to do that in a different color. So let's do that in red. Okay, so the noble gas method, noble gas electron configuration. Okay, in this case, notice that we have a pattern here. Look at iron. Right up to here, the 3p6, okay, 3p6, that's the electron configuration for argon. That's a noble gas. Noble gases don't react. They have complete electron shells. So if you were to look at hafnium, and if you notice that hafnium, the noble gas that's above its row, so here's the row for hafnium, hafnium's in this 6th row, 6th energy level, there's xenon. Well, what we could do for hafnium, instead of writing this all out, we take a bracket, we write xenon, the noble gas. That's the row above the particular element that you're interested in. And then we take this little piece, because see, this electron configuration right here, where it ends at 5p6, that's the electron configuration of xenon. So why write that all out? We know that's a complete filled orbitals. So let's just write the electron configuration just before hafnium is landed upon. So instead, it'll be just 6s2, 5d2, 4f14. Done. No crazy writing, no crazy arrows. It's quick, it's easy, and totally doable. We could do another one real quick. Let's try technetium, TC, number 43. 43 electrons. Check this out. Technetium, I just circled it. Krypton, number 36. That is the noble gas before that particular row, so I'm going to write that down, Kr. And then all I need to do is 5s2, and then I'm in the 4d block, 4d, 1, 2, 3, 4, 5, and 5s2, 4d5, and I'm done. Technetium and electron configuration is written. So hopefully this will help you. Enjoy and study chemistry. Until next time, bye.